complexity series. It's going to be given by Nicole, who is going to become a faculty member at Michigan. So congrats. And without further ado, please take it away.
Okay, hi everybody. It's nice to be here. So I'm here as a Simons Fellow for this semester, and then later I'll be at Michigan. Before that, I was a PhD student with Virginia, who you just heard speak. Okay, so Virginia talked in her talk about kind of an overview of fine-grained complexity and the different types of areas and problems it can be applied to. And in this second talk, what I'm going to do is zoom in on one of the particular areas that it has been particularly successful in, and that is distance problems in graphs. Okay, so today we will see some examples of fine-grained hardness for distance problems in graphs. And I've heard from the organizers that these problems can be expressed naturally as recursive database queries. So if that's a motivation point for you, then great. And if it's not, then that's also fine. So just as a first thing, like I don't generally work in databases or logic. And so I want to make sure this talk is clear to you. And so if I have different terminology than what you're used to, then I hope that you will clarify. Okay, so what I want to start with first is like a more broader takeaways from fine-grained complexity, since this is like the boot camp of the like introduction to fine-grained complexity. And some of these will appear later, and this is kind of like a preview of what I view as some of the broader takeaways. So the first one, which Virginia mentioned, is like oftentimes we find that like the textbook algorithm turns out to be the optimal one. But there are, of course, cases where the textbook algorithm is not the optimal one, and fine-grained complexity can also help us figure out when that's the case. So one point here is that like even if all of these conjectures and stuff turn out to be false, this has still been a useful tool in terms of finding algorithms because, for example, people have looked at the whole landscape of all the problems we've been able to prove hardness for and said, wait, here's a problem and we can't prove hardness for it, and so maybe we can get a better algorithm. So it helps tell us which problems that we really need to focus on working on for algorithms. And this has come into play in some of like the recent breakthrough works. Talked to some of the authors on like max flows and stuff. Okay, second takeaway is that, you know, some fine-grained complexity reductions have this nice property that they're actually simple enough to be taught in courses. The one Virginia showed you earlier, I would say is, and I'm going to show you some also that are. Of course, there are some that become very involved and complicated, but like the fundamentals of this area, I would say are accessible. And that's a nice property that we can actually be teaching people who have just taken like one undergrad algorithms course, like some of the fundamentals of this. Okay, another takeaway I would say is that there are some like surprising types of reductions in fine-grained complexity. So one of them is like that you can kind of make an assumption about an exponential time problem and then get as a consequence something about a polynomial time algorithm. And that's what you saw earlier today with Virginia reducing from the strong exponential time hypothesis about KSAT down to the orthogonal vectors problem, which was in polynomial time. So that's kind of maybe surprising on first glance that you can do that. A second one is that you can go from large output sizes to small output sizes. So for example, what you're going to see today that I'll talk about later is you can go from all pairs shortest paths where the output size is n squared. And then you can reduce that to a problem where the output size is just this one number. And maybe that seems surprising on first glance, and I'll show you an example of that. It's the negative triangle one that Virginia mentioned earlier. And then a third type of maybe surprise is that you can kind of take one single assumption that has that's just about the exact time complexity to get an exact answer for a problem. And it turns out that we can transform this into getting lower bounds for conditional lower bounds for like whole like time versus accuracy approximation trade-offs just by like making this one exact algorithm assumption. And you'll see also an example of that later. I would argue that fine-grained complexity is an exciting field with active new developments, and that's another possible takeaway. And then finally, you know, maybe given this introduction to this field, you can find some of your favorite problems and see if they're viewable through the lens of fine-grained complexity or not. Okay, so with those high-level things, let me now get down to some actual definitions of problems, etc. So again, we're talking about distances in graphs. And the first parameter that I want to define here is the eccentricity of a vertex. So we have a graph, and then the eccentricity of a vertex is just going to be the farthest vertex from that one. The diameter is going to be the maximum eccentricity in the entire graph. The radius is the minimum eccentricity in the whole graph. And here's a picture that might help. So the diameter is just going to be like the single largest distance in the whole graph. And the radius is the one with the minimum eccentricity. That is to say, there's some vertex called the center, for which it is distance at most radius from everybody else in the graph. There's also this parameter called median, where it's the minimum over all vertices, and then you take the sum of the distance to everybody else. And the point here is that actually something that might seem surprising at first, if someone is not familiar with these algorithms, is that like the best thing that we know how to do to compute these things, you just want to find the diameter. You just want to find the one single biggest distance in the graph. The best thing we know how to do is to compute all of the distances in the whole graph, write down all of them in like an n by n matrix, and then just take the biggest one. And that's the case for all of these different problems. And so in particular, that's going to take time like n cubed for dense graphs, where you have like n squared vertices, n squared edges. And then for sparse graphs, that's going to take like n squared time to run all pair shortest paths. So these are like the two running times that we're working with, and that we want to show hardness to say, in dense graphs, you can't do anything better than cubic, and in sparse graphs, you can't do anything better than quadratic. Okay, so that's the question here. And then there's another question, which is maybe we want to approximate these things, and we can also ask the similar questions. Okay, any questions so far?
What about the regime of M is in between N and
Oh, good question. Oh, thank you. Yes, so the question was about, I've just mentioned dense and sparse here. What about the regime when your density is in between these things? So at least for the sparse reductions, we don't know how to make them any better for a denser graph. And similarly for the dense reductions, maybe I'll pose, Virginia, if you know anything about things in between. I don't think I do.
It's depending on what assumption you make. About things in between. From the assumptions we work with, we just get things for these two endpoints.
Yeah, it's a good question. Okay, so the outline of today is that it's going to be split into two parts. First, we're going to look at sparse graphs, where M here denotes the number of edges, and that's approximately the number of vertices. Then we're going to look at dense graphs. And these are almost going to be like two totally separate talks. Even though we're talking about the same problem, somehow the sparse and dense regimes are quite different. And, it's maybe an open problem to kind of understand maybe more relationships between them. But for now, they're actually, you're going to see two quite different kind of talks. Okay, so let's start with sparse graphs. Okay, so in sparse graphs, again, the question is, can we solve these problems that we care about, eccentricities, diameter, radius, median? Can we solve them in a subquadratic time? That is like n to the 2 minus epsilon. And the answer turns out to be no, under some hypotheses. After that, we can ask the question of, what about approximation? What if we only care about returning a solution that's within, let's say, a factor 2 of the true diameter, for example? And it turns out the answer is yes. You can get some very interesting approximation algorithms here that are subquadratic, but it only works up to a point. And you can show also lower bounds, conditional lower bounds that say, under some hypotheses, you can't get anything better than a particular accuracy of approximation. Okay, so let's be a bit more specific here. So these are the best known approximation factors that we have for subquadratic time algorithms. For diameter and radius, you can get a 3/2 approximation. You can do this in n to the 3/2 time for a sparse graph. For eccentricities, the approximation ratio is a bit different. It's 5/3. For median, you can do 1 plus epsilon and m over poly epsilon time. And we're asking the question of, are these things tight? And it turns out, yes, they are. So we can show that these particular approximation factors are tight under certain hypotheses. So what do I exactly mean by that is, if I want to get anything better than like a 3/2 approximation for diameter, then suddenly I need n squared time. That's what it means for these factors to be tight.
And the running time too.
Yes, you can also show that for these particular algorithms, if you want to get anything better than this running time, then the approximation factor is going to go up. Okay, so this is kind of what the world looks like in the sparse regime. So earlier today, you saw this reduction from KSAT down to OV that Virginia showed. And then what you can do here is take OV and reduce it to this 3/2 minus epsilon approximate diameter, as well as eccentricities. It turns out that we need a bit of a different hypothesis to deal with these other problems, radius and median. We call this the hitting set hypothesis. I'm not going to define it here, but it's similar to OV, but it has different quantifiers, like different for all there exist quantifiers that kind of match the quantifiers in the radius problem. And for that, you can get a reduction from here to here. Okay, so what we're going to see today is I'm just going to focus on bringing OV, reducing OV to diameter. And this is one of those reductions that's actually simple enough to be taught in a class. And furthermore, I know that some people teach in classes like first going from KSAT to OV that Virginia showed you, and then going from OV to diameter. And I think that's a really nice example nugget of fine-grained complexity. Okay, so let's get into this. So let's first recall what the OV hypothesis is. So it's the orthogonal vectors problem. And we're saying, given a collection of capital N binary vectors of length roughly log n, is there an orthogonal pair? That is there a pair with dot product 0? The way that I really want you to think about this problem is kind of ignoring this and just looking at this. So what we can imagine is that each vector is like the indicator vector for the presence of elements in a set. That is to say, we have a universe of size log n. Each of these vectors is expressing, I have this element, I do not have this element, I have this element, and it represents a set. And then all we're asking here is there a pair of disjoint sets? So this is like a set disjointness problem. Is that okay? Okay, so the OV hypothesis again is that OV requires quadratic time, where n here is the number of vectors. Okay, so you already saw also that the strong exponential time hypothesis implies OV, so any reductions we can get from OV also follow from the strong exponential time hypothesis. Okay, so now I'll show you the reduction. And this is a reduction from OV to approximate diameter. And our goal is to say the following. We'd like to say that anything better than a 3/2 approximation for diameter, if you can do that in time subquadratic, then you can get an algorithm for OV that is also subquadratic. So that's our goal. Yes?
The tilde here?
Oh, the tilde is suppressing log factors.
You can change one epsilon to an epsilon prime and remove the tilde.
Yeah. Okay, so here's the construction. So we're given an instance of OV, which is a collection of sets here, collection of subsets of a universe of size log n. And what we're going to do, we're going to create the following graph. There's a vertex here for every element That is to say every index of the vector. So this is like the ground set that we're picking from, A, B, C. And then there's also a vertex for every one of these sets, aka the vectors. And so these sets could be, for example, A, B, C, A, B, etc. And we're just going to add edges in the natural way. That is, we're just going to add edges from this set to each of the elements. So from here to A, B, and C. From here, we add an edge to A and B, etc. And that's the entire construction. There's also a clique here. So imagine all of these vertices here are in a clique. There's an edge between all of them. Okay, so that's the entire construction. And now we would like to show that if you can get a better than 3/2 approximation for diameter on this particular graph, then we've solved OV. So let's consider the two cases. Let's first consider the case where there is no pair of disjoint sets. And my claim here is that in this case, the diameter is 2. So why is this the case? This is the case because we can say, okay, if we don't have any pair of disjoint sets, then every single pair of sets here shares some element, and therefore both of them have an edge to the same element, and then the distance between them becomes 2. Okay, and then you also need to consider other types of pairs of vertices. So for example, pairs of vertices in here, those all have edges between them. So those ones are also of distance at most 1. And then also one vertex in here and one vertex in here. Again, they have distance 2 because you can take an edge here and then take one of the clique edges. Okay, so this shows now that if you do not have a pair of disjoint sets, then the diameter is 2. Okay, now we need to do the other side. So now we're going to say if there does exist a pair of disjoint sets, then the diameter is at least 3. That's the claim. And the reason is, okay, let's look at these two sets. They are disjoint. Now, what does that mean? That means that there does not exist any element in here such that they both have edges to them. So there's no path of length 2 between them like this. And therefore, their distance is at least 3. And so the diameter is at least 3. Okay, so now to, yes?
Well, not exactly 3. I thought we have a click on the right-hand side, so it should be...
Yes. Yeah, you can definitely get from here.
Consider the empty
3.
set.
What did you
We
say?
have the empty set. Anyway. The empty set won't have an edge to the clique.
Oh, I see.
Whatever.
Corner cases.
If you remove it, then you're fine.
Yeah. Thanks.
Okay, so now to conclude the proof, what we're saying here is that if you had an approximation algorithm that gave you a multiplicative approximation factor better than 3/2, then what does that mean? That means that you could apply it to this graph and it would distinguish between the cases of diameter at least 3 and diameter 2. And therefore it would tell you which of these two cases you're in and tell you whether or not there exists a pair of disjoint sets, thereby solving OV. Okay, are there any questions about this reduction? I'm happy to answer anything.
I'm lost about the role of the sparsity here. Should we think the graph is being dense, sparse? I think I lost track of that.
Good. So this is for the sparse case. So it's important that we construct these graphs so that they are sparse. In particular, these graphs are sparse, and we're allowing log factors. So these graphs are sparse because the size of this is only going to be log n. And so the number of, every vertex here only has degree at most log n. And so the total number of edges is, n times log n or so.
I think the point I was missing is that if the graph is dense, then you're allowing yourself a higher complexity to solve the diameter problem.
Yes, if the graph is dense.
What changes with this reduction if the graph is dense?
What changes? Okay, yeah. So this shouldn't say anything about dense graphs. This tells you that you can't solve diameter any faster than n squared. Sorry, you can't get an approximation any better than n squared. We already okay.
Yeah, but if you allow the graph to be dense, then you're saying, well, I can run in time and cube. And then this reduction doesn't say anything interesting.
Just creating a graph will take you quadratic time. It's not going to give you anything better than quadratic OV. So
I mean, the statement is kind of backwards for dense graphs.
Exactly, yeah. No, the graph is the same.
But anyway, the graph is sparse. The graph produce is
but
sparse.
the reduction will take in square time if it's dense, so then you don't get anything.
Why is that?
Because if
No.
you make it dense, the running time will be is the number of edges it creates, and if dense means n squared.
It's important that this is a reduction from low dimension OV. Right, I mean, you can think of other dimensions, but that's what governs the size of the clique on the right-hand side, is the dimensionality.
Right, so you're saying that if the dimensionality.
You
were
can
much
have a
bigger-
larger dimension and you get another problem, yeah.
No, I think the confusion that logicians had is keep the same dimensionality, but replace sparse graphs with the statement about sparse graph is statements about dense graphs. So what changes on this slide?
What's changed is the theorem is trivially like false implies false.
Exactly, yeah, so then you get,
So it's still true, but like, who cares?
yeah, it's backwards, it's not the.
Yeah, because you can't get less than x squared on this graph.
But we got it, thank you.
Okay.
Okay. Anything else?
You can also think of it as if the size of the graph is m, the number of edges, then it will be about beating m to the 2 minus epsilon instead of n, right? Because the number, okay, you can think of it that way. It won't be dense, but it will be in terms of the number of edges.
Okay, so now I want to just tell you, without proving anything, some of the newer developments about the diameter problem. And these are things that have happened just within the last couple of years and are still actively happening. And so what it turns out that we can do is get a time versus accuracy trade-off just by assuming the OV hypothesis. So my goal is not for you to understand this whole picture, but I just want to point out some important things in it. So on the x-axis, there's the approximation factor. On the y-axis, there's the running time exponent. So for example, and all of these points here are known algorithms, and all of these boxes here are known conditional lower bounds. That is to say, if you have one of these boxes, what that means is that conditionally you cannot get an algorithm that's going to fall into one of these boxes. Okay, so what this is saying is like, you know, if your approximation factor is 1, that's just for exact algorithms. This is just the trivial run all pairs shortest paths n squared time algorithm. And it turns out that you can get some subquadratic time algorithms, which are these ones. And then as you go down, the approximation factors get worse and worse. And this work has been able to get some, it's not completely tight, but some of these points are tight. And we've shown that there's like if you believe Seth, then there's an inherent time versus accuracy trade-off. Some of these trade-off things are only for undirected graphs, and just in very recent work, like a couple months ago by Virginia and others, they showed that for directed graphs, you can also get some trade-off.
So do these algorithms specifically assume sparsity, or does it like happen to run in n quadratic time if the graph?
Yeah, good question. So the question is about how the algorithms depend on the sparsity. So for example, this algorithm runs in time m times square root of n, where m is the number of edges. So if you have a denser graph, then you do get that m times square root of n.
Is it easy to see why what you showed on the previous slide implies something for a truly multiplicative bound? Like if I allowed a +1, why doesn't the construction collapse?
Okay, so you're asking about like, you want to have a reduction that gives separation instead of between 2 and 3, between like 2L and 3L for any value of L, for example. It turns out that you can do that, but you need like you can add a couple of extra gadgets to the graph and you can get that. Good question.
Is the point at the bottom right trivial? The fact that it can have two approximations?
This one. Yeah, so what you do is you pick an arbitrary vertex, run Dijkstra's algorithm from it, and just take the biggest distance. And then you can show that in like one step of a proof by the triangle inequality, this is at least half of the true diameter, which gives you a true approximation. And one of the kind of cool things about this recent work is that it actually showed that if you restrict yourself to linear time algorithms or near linear time algorithms, the best you can hope for is just that trivial algorithm. Okay, so now if there aren't more questions, I'm going to move on to the second part of the talk, which is disjoint from the first. It is about the dense graph regime when the number of edges in the graph is about n squared, and we're trying to beat cubic time. Okay, so now the question that we're asking is, can you solve these problems, eccentricities, diameter, radius, etc., in subcubic time? And the answer here turns out to be kind of interesting. It turns out to be no, you can't do it under the all pairs shortest path hypothesis that Virginia mentioned earlier. However, it's actually not known for diameter. So for all of these other ones, radius, eccentricities, etc., you can show that they are actually subcubically equivalent to the all pairs shortest paths problem. But we don't know for diameter, and this is one of the big open questions in the area. For all we know, diameter on dense graphs could be in n squared time. Okay, so here's the theorem. All pair shortest path is equivalent to radius, median, and other problems under these subcubic fine-grained reductions. And you'll notice that this is actually different from the sparse case in the sense that in the dense case, we're actually showing equivalence. We're showing it in both directions. In the sparse case, we were only showing it in one direction, from OV to diameter. And so in the dense case, we actually have this kind of whole web of equivalences between a bunch of different problems. And let me just clarify what the definition of equivalence means. It's that if you have a truly subquadratic time algorithm for problem B, it can be converted into a truly subquadratic time algorithm for problem A, perhaps with these epsilon and delta being different values. Okay, so now let me show you, before I show you what the world looks like in terms of the web of reductions, let me say a little bit more about this all pair shortest path hypothesis, which is that you can't do anything better than, you can't do it in truly subcubic time for weighted graphs, like Virginia said. And this is kind of some evidence that it might be a hard problem. There's just a very long line of work that was shaving logs and shaving more logs until Ryan told everyone, okay, you can stop shaving logs now. Okay, so this is a big open problem. Is all pairs shortest paths in truly subcubic time? And this is what we use as our hypothesis, that it's not. That's the APSP hypothesis. Okay, so now here's the web of reductions for dense graphs. And you'll notice that this is a strongly connected graph. And so what that means is that everybody on this screen is actually subcubically equivalent to everybody else. And there's a bunch of different problems, and I won't define them all. So you start with the APSP hypothesis, and then what we're going to see today is this part of the picture. We may not get all the way to this one, but what I really want to communicate to you is how to get from APSP to negative triangle, because that was, as you can see from this picture, a very influential result by Virginia and Ryan from 2010. And you can see that once we had the reduction to negative triangle, you can go from here to everybody else. And this is like a significant step because for APSP, you'll notice that the output is of size n squared. And suddenly for negative triangle, all you're trying to do is return like one bit. Is there a negative triangle in the graph? Okay, so my main goal for this second part is to show you some ideas for how to go from APSP to negative triangle. Okay, so the first step is to go from APSP to this distance product that was mentioned earlier. So that's this arrow. This is kind of the, I guess, more definitional, less interesting part of the reduction. It has been known since 1971. It's basically saying that there is a distance product that can exactly capture APSP. And in particular, that product is defined as follows. So like in regular matrix multiplication, you're doing multiplying and adding, whereas here we're doing adding and taking the minimum. So this is a product that you can take over two matrices. And the statement here is that these two, like APSP and this distant product, are actually equivalent. And for what we're going to do today is to reduce from distance product to APSP. Okay, so what you do here is you take your instance of distance product. You're given these two matrices A and B that you want to take the distance product of. You take the, and then you consider that as the weighted adjacency matrix of the graph. So you say that the number in the UV position of the matrix is going to be considered the weight of the edge from U to V.
I think you're going from APSP to distance.
Yes, that's what I realized just now as well. Thank you. Okay, so this is like the wrong. This thing is the proof for the arrow in the other direction. I'm just saying the words wrong. Thank you. Okay. Okay, so we're given an arbitrary instance of the distance product problem, and we want to.
No, it's from graphs.
Wait.
If you can solve distance product, you can solve shortest path. So you take shortest path.
Oh, this arrow is not it's the opposite direction of the previous slide. Okay, thank you. Good. So we're given an arbitrary instance of all pair shortest paths. We would like to convert it into an instance of the distance product. So what we're going to do is we have our graph, we have all the weights on our graph. Now we're going to construct a matrix. This matrix in the UV entry is going to have an entry that has weight UV, the weight of the edge UV. It's going to have infinity for the non-edges, and it's going to have 0 for U equals to V. And what you'll notice, if you stare at this for a little bit, is that if you take the kth power of the matrix, then what you're going to get is the weight of the shortest path on at most k edges in the graph. Because if you think about what a shortest path is in a graph, it's like I can go from a vertex to another vertex through an intermediate vertex, and I'm going to take the sum over the two edges, and I want to take the minimum intermediate vertex that gives me the shortest path. Okay, so how you can get this is by doing successive squaring of this matrix to get all the way up to a to the n, which would give you the weight of the shortest path on any number of edges in the graph. And this successive squaring is just going to add a log factor to the running time.
Sorry, so by squaring you mean use the distance product oracle to square?
Yes. Okay, thank you for the correction. I hope if I confused you, which is totally valid, I can go through it again offline if anyone is. Okay, yes.
Just to conclude, so it means that if I can solve the distance product in quadratic time or better than quadratic time, then I can solve
Cubic.
distance product in better than cubic time. Then I can solve a PSP also in better than cubic time.
Yes.
Okay, thank you.
And this is matrix multiplication on the tropical semi.
Yeah.
Yes. Yes.
What Fukion is asking, we can think about the distance product over the tropical semi-ring and APSP is also required in a tropical semi-ring. So can we make this reduction be or leave it to the setting we're using and switch to another setting? Perhaps it says something about the complexity of these problems.
There's a paper, I think maybe it's Fisher and Meyer, where so this shortest path is the transitive closure under the semiring, right? And so if you take a different semiring, a similar sort of reduction would work under some conditions
On the semitic.
on the semiring.
So for a class of semirings, this problem is equivalent.
Yes. And in fact, Fisher and Meyer got rid of the log.
Yeah, you can get big O of T then.
Yeah. There's corruption.
Okay, good. So now comes really the part that I want to emphasize here, which is how do you go from this distance product down to this negative triangle problem? And you can do it. And so just to define the negative triangle problem, we're just asking, given a graph, it has weights. Some of the weights can be negative, and we're asking, is there a negative weight triangle in the graph? So you add up all the edges in the triangle, is it negative? You can do a cubic time algorithm by trying all triples. And what we're showing here is that you can't do significantly better than this trivial algorithm if you assume the APSP hypothesis. Okay, so there are two steps to this reduction, and there's an intermediate problem. And the intermediate problem is perhaps what you would expect the intermediate problem to be, maybe, which is that you can go from distance product to all pairs negative triangles. That is to say, for every pair of vertices in the graph, we want to output, is this pair in a negative triangle? And then the second step is the step where you're going from the output size being n squared to the output size being just one single number. You're going from all pairs negative triangles to just asking, is there a negative triangle? So first, let's look at the first one. So our goal here is to go from distance product to all pairs negative triangles. And the reduction is the following. Okay, so what we would like to do is we're now given an arbitrary instance of distance product. We would like to create a graph out of it such that if you can solve all pairs negative triangles on this graph, then you've solved a distance product. Okay, so let's look at this example. These A and B, these are the two matrices that we would like to take the distance product of. And what we're going to do is just make a graph that has three pieces, and we're going to add edges from, let's say, from like I to K that have, so I'm going to add an edge from this first vertex to this first vertex with weight 1 because there's a 1 in the position 1, 1. There's a 5 in the position 2, 1, and so I'm going to go from the second vertex to the first vertex with weight 5. Is that okay? So then on the other side, I'm going to be doing exactly the same thing, but now I'm going to be considering the weights 3, 2, and 2 inside of this matrix. Okay, so now what we would like to show is that if you can solve all pairs negative triangle, then you can solve distance product. And to do that, we need to add some more edges to the graph. In particular, we need to add some edges of negative weight. So what we're going to do is add some edges in this direction to form some triangles here. And these edges are going to have some carefully chosen weights. So in particular, you'll notice that I'm adding an edge in this direction. It has weight -8. And you can see that there's a path of 2 and 2. So this is a negative triangle. And if I were to change this weight to like -4, then this would give me a triangle of exactly 0. But if it was -5, it would give me, yes, there's a negative triangle. So that is to say, if you set this to -5, you get the answer yes. If you set it to -4, you get the answer no. And so our goal is to find the threshold of when the negative triangle, when there is a negative triangle and when there's not a negative triangle. And that tells us what is the distance between these two vertices, which is what we want to compute. Okay, so the way that we're going to do that is we would like to find like the special edge weight for each one of these edges going in the backwards direction. And what we're going to do is a simultaneous binary search. That is to say, we're simultaneously doing a binary search over all possible edges in this direction. And we only need to repeat this log n times because the binary search is only going to take log n calls to negative triangle. And then in the end, you get that if the weights are at most polynomial, then only log n calls to negative triangle, to all pairs negative triangle suffice. So every time you call all pairs negative triangle, you get an output of an n by n matrix, which tells you for each of these pairs, is there a negative triangle? And then you adjust the weights accordingly. Is that okay? Yes.
How many red edges?
So you're adding red edges for, good question, because there's only 2 in this picture. So you're adding red edges for all of the different pairs. So I'm adding like the size of j times the size of I. For every possible one of these pairs, I'm adding a red edge, and I'm doing simultaneous binary search over all of them.
Sorry, so in the distance product instance, you're using numbers integers 1 through n and infinity? Those are what's the range of entries that you're using?
Yes. Yes, that's what I'm using.
The range is polynomials here. Over there it says n to the c.
Okay, that's it. That's
And infinity.
I think I'm lost with the simultaneous binary search. Can you please explain this again?
Yes. So let's just look at this one edge. And do you agree that we can do binary search by doing log n calls to all pairs negative triangle?
Absolutely.
Every time we get the output of all pairs negative triangle, we look at the ij entry and we say, did this tell me yes or no? And then I adjust this weight accordingly until I find the correct threshold between yes or no. So now I'm going to do that simultaneously for all of these. So I pick a weight for all of these edges. Then I get my output for all pairs negative triangle. And my output is of size n squared. So it tells me whether or not there's a negative triangle for all of these different pairs. And then I look at that matrix. I look at which ones were and which ones weren't negative triangles. And then I simultaneously update all n squared of these edges at once.
So I think the important bit here is that you don't get a yes or no answer. You don't get the binary answer, but you really get a report of all the negative triangles.
Yes.
I see. Then you know which ways you want to adjust up or down to find it.
Exactly. So importantly, he noted that this reduction here is to all pairs negative triangle. So we're really using the fact that the output is all of the pairs negative triangle. And next, what we're going to do is reduce from all pairs negative triangle down to just the binary answer of, is there a negative triangle? We haven't done that one yet.
But is it one call or several calls in the way you had set up?
Right now it's order log n.
Log n.
So you have weights that are up to n to
Log
the
n
c.
calls, yeah.
Okay, so now we're moving on to the second part where we're trying to reduce all pairs negative triangle down to negative triangle. This is the part where the output goes from size n squared to just 1 bit. Okay, so this is just what we showed in the first reduction. Okay, so now our goal is the following. All pairs negative triangle to negative triangle. And we would like to take an instance of all pairs negative triangle and solve it using an algorithm for just negative triangle. And the way that this works is the following. So we're going to have to make like a bunch of instances of negative triangle because each of them is only going to give us 1 bit. And in the end, we need n squared bits. Okay, so what we're going to do is we're given an instance of all pairs negative triangle. We take this graph and just imagine that we copy the graph 3 times. And I'm going to just put an edge between like this vertex A1 to A2 if there was an edge from A1 to A2 in the original graph. So far I'm just doing kind of a trivial transformation to take this graph and make it into a tripartite graph so that all of the triangles are going to go between these two. So now this graph actually has more triangles than the original graph because I'm like copying each one, but that's fine. All we need to find is for each pair, does it have a negative triangle? Okay, so what are we going to do? We're going to take each of these copies and we're going to split it into different pieces. And each of these pieces are going to be of size S. So this one is of size S, size S, size S. We do the same thing with all of these. And then what we're going to do is to consider all n over s cubed triples of pieces. So I could take this piece with this piece with this piece, and that's going to be one instance of, or maybe we're going to then find the negative triangles within each triple separately. Okay, so we have created multiple instances now. We've divided into pieces, and we're going to consider each triple separately and do a separate algorithm for each one, which is going to involve some calls to negative triangle. So this is kind of the high-level idea. And now let me say a couple more details about how you actually implement this. So what we do is, remember again, we're trying to solve all pairs of negative triangles. So our output is going to be an n by n matrix where every entry of the matrix is going to correspond to, is there a negative triangle with this that contain this particular pair of vertices? So we're just going to initialize our matrix to be all zeros, and then we're going to gradually fill it in. So we're going to do for every triple, for every one of these triples of pieces, we're going to say, run negative triangle on it. It might return yes, and it might return no. If it returns no, then we know that there's no negative triangle in these particular pieces, and we can just zero out that section of the matrix. On the other hand, if it returns yes, then we know we have found a negative triangle, but it might not be the only negative triangle that's in these particular pairs. So what we're going to do is we find a negative triangle here. And then we're going to set that entry of the matrix to 1 because we successfully found a negative triangle. And then we're going to set the weight of this edge now to infinity. And when it's set to infinity, that means that it's no longer going to belong to any more negative triangles. That is if we...
Sorry, I'm lost again. Are X, Y, Z's indices of groups or of individual nodes?
So they're individual nodes. So I ran negative triangle on groups, and I found a specific negative triangle on these 3 specific nodes.
No, the X, Y, Z are over the groups. The A, X, A, Y, A, Z are the nodes.
Yes.
In this slide.
Yes.
So AX, AY, AZ, each of these is a vertex.
In group IX, JY.
Yeah, so there's 3 groups on each of them. So X ranges from 1 to 3, Y 1 to 3, Z 1 to 3.
Did that answer your question? Okay, good. So let's go again.
Indices of groups. They're indices of groups and a little overload in notation that AX is the node that you found in IX, AY is in the node in JY, and AZ is the node in KZ that you found.
I see. So the assumption that the oracle I'm using is not going to report yes, no, but actually it's going to report it's going to give me one negative triangle.
Good, but if you actually you can say it, right? He says if you can detect, you can find. So we haven't said that. So you can say it.
Yeah, see, this thing assumes you can find, but there's another exercise for the listener to.
There's an exercise to the listener that if there's an algorithm that can detect a negative triangle, then you can also find one at the same time, roughly.
It's like the self-reducibility.
Self-reducibility, exactly.
ChatGPT might help me here.
Okay, I'm not sure. Let me just do a little summary of that for everybody. So the last thing that was said was when we run negative triangle, we've just assumed that we actually got a negative triangle back. But the definition of the problem is just telling us, does there exist a negative triangle or does there not? So really what we're getting is just, does there exist one in these 3 squares and does there not? But as Ryan mentioned, it's an exercise for the listener to also go to the search problem. So the claim is that if you can actually detect whether or not there is one, then you can actually find it as well. And I won't say how to do that, but for this reduction, we are assuming that we're actually given the real triangle. Okay, so what have we done so far? We took each one of these triples and we asked, does it have a negative triangle? And it returned a negative triangle if the answer was yes. And the negative triangle could, for example, have been A3, A4, A5. Then what we're going to do is set the weight of A3, A5 in this graph. We're going to update the weight to be infinity. The reason we're going to do that is so that if we again call negative triangle on this same three pieces, we're not just going to find the same negative triangle over and over again. So we need to set the weight to infinity so that it's going to return a different negative triangle until we found all of the negative triangles. Okay, so just to clarify here, you might, so we only need to find the negative triangles that involve pairs. So to solve the all pairs negative triangle problem, we only need to find the negative triangles that involve one vertex in I and one in J. We don't need to worry about the ones that are like in these different pairs. And the reason for that is because I just made a copy of the whole graph. So we're only caring about the pairs where one is in here and one is in here. And for that reason, we're allowed to just set the weight of of this edge to infinity when we found a negative triangle, because this edge does not participate in any of the other negative triangles that we're trying to find between I and J. Okay, so this is the algorithm, and then at the end we return this matrix C. And again, the reason that we're setting it to infinity is so that we just keep on running the negative triangle algorithm until it returns no, in which case we can stop. And we do that separately for each one of these triples. Okay, so now you can do the running time analysis here, and you can say, okay, what is the running time? Well, it's the number of triples, because for each of the triples, we ran a negative triangle algorithm. But then additionally, every time we found a negative triangle, we ran it again on that same triple until we didn't find any more. And so the running time is going to be the time for negative triangle times the number of triples plus the number of triangles that we found. Okay, so now we can kind of do some parameter balancing, and the number of triples is n over s cubed. The number of triangles is at most n squared, because it's all pairs negative triangle, which then there's at most n squared pairs. So let's suppose negative triangle is in time capital N to the d, where n is the number of vertices in the graph. Then this becomes the following running time if we set s to be n to the 1/3, and we did that to balance the parameters. And what this means is that this running time is subcubic if d is less than 3. That is to say, if you have a subcubic time algorithm for negative triangle, then this whole entire procedure runs also in subcubic time. Okay, are there any questions about this?
And still the puzzling thing of if you know that there is one, you can find one. Is it because you took small groups? I mean, does it appear in the algorithm? Yes.
Yeah, there's a reduction that also partitions into groups.
So
you call the detection on the groups.
trade-off of parameterizing the S. This is where it plays a role.
And that's a separate
No,
reduction
this
entirely.
is it's a self-reduction. You split into two groups, each part, and then you only recursion one, the one that says that it contains one.
I think your question was, Can you do the search to detection reduction even if your graph is not these small groups, if it's
Yeah.
the whole graph? And the answer is yes, you can still do it.
For sure.
Yes.
What is S in this picture?
Good. So in this picture, we're making, so S is going to be the size of each group. So we're splitting these into pieces of size S. This is S, and then at the end, S is going to be set. So S is 2 here, but it's going to be set to n to the 1/3 in general. Anything else?
So does the construction work for undirected graph?
Yes.
Okay. Even for the distance product to all pair negative triangle.
Yes.
Good question. Yes. Question was, does it also work for undirected graphs? And the answer is yes. Okay, so now, in the interest of time, let me say something a bit more high level. So I'm not going to go through the reduction from negative triangle to radius. If you're curious, you can come talk to me or Virginia or Ryan. So there's going to be like a pretty complicated picture coming up, which you can ignore. And now let's talk about something a little bit more high level. So just in general, we talked about these two problems of radius and diameter. And it turns out that in the literature, anytime we can find an algorithm for diameter, it turns out that it has carried over to radius and vice versa. But the same is not true for these conditional lower bounds. And in particular, these two problems differ in like the quantifiers, like max versus min max. And this seems to kind of create some issues for making these lower bounds. And in particular, you'll recall that in dense graphs, we have a reduction from APSP to radius, but we don't know how to make it go through to diameter. So that was the part, the part where you go to radius, that was the part that I didn't show you. So if you want to get a sense for why it might not work for diameter, then we'll be happy to talk about it offline. And then it also turns out that we know some problems that are equivalent to diameter in dense graphs. So we know something, but we just don't know whether you can reduce from APSP to diameter in dense graphs. And then on the other side of the spectrum, it turns out that in sparse graphs, we have like this whole time versus accuracy trade-off. There was that picture. We have that only for diameter, and we don't have it for radius. And so it's kind of interesting that like in dense graphs versus in sparse graphs, radius and diameter seem like diameter is harder than radius, or so it seems in one regime, and the opposite is true in the other regime. So these pose some interesting open problems that I'll put here. So these two first open problems are trying to get radius and diameter to match up with each other. So can we get hardness for diameter in dense graphs, and can we get approximation trade-off hardness for radius in sparse graphs? Let me mention also a couple more open problems. So this is the thing that was brought up earlier, but about like sparse versus dense, and so far we're kind of have these reductions that work in either case, and maybe there's some way to unify it a bit better. And then there's also this question of approximation in dense graphs. We only talked about approximation in sparse graphs, and these dense graph reductions don't preserve approximability. And then you can also, if you're particularly interested in diameter, and there's a whole bunch of different variants of diameter, et cetera, that Yinjun has worked on as well, you can look at my PhD thesis, and there's an open problem section, or I can send it to you. Okay, thank you very much. Let me put up these takeaways.
More
again.
question?
Are there interesting separations between directed and undirected graphs in this world?
Yes, there actually are. So to give you one particular example, it turns out that if you consider radius in the sparse case for directed graphs, and versus radius in the sparse case for undirected graphs, it turns out that for directed graphs, you can get a very strong lower bound, which says that basically there's this like linear time algorithm that we know. And if you want to get anything better than the approximation factor for this linear time algorithm, it immediately jumps up to n squared. That is to say, in the picture for diameter before, it was like this whole staircase thing, but for directed radius, it's literally just like that. And the same, and for undirected radius, this is an open problem. But we, I guess, kind of suspect that it should be similar to undirected diameter where you get the whole trade-off.
Are there any fine-grained complexity results for tree width? When you fix the tree width, you tend to decay, but you don't seem to know better.
Yeah, good question. So the question was about tree width, so parameterizing by the graph parameter tree width and whether there's fine-grained reductions known for this. So there was actually a paper from 2016 with Virginia and 2 others where they studied in particular diameter for bounded tree width graphs. And they showed that you can get some subquadratic time algorithms for exact diameter if you parameterize by
Actually, my question was the other, detecting tree width. If I give you a graph and the number k and I ask you is the tree width at most k, the algorithms are then to decay as far as I know.
Yes.
Is that a fine-grained complexity there?
For the exact case, yeah, I think
For
so.
exact case.
For approximations, you can get C to the K.
Yeah, C to the K for approximation is the constant approximation. And C to the K times N. No. Parameterized complexity.
Any other question? Is there another, so if the graph is dense, and I would like to beat the cubic boundary, is there, I guess you mentioned tree width, but is there a more natural parameter of the graph that allows us to
So you're asking about computing APST in subcubic time.
Subcubic time
if you
for dense
assume-
graphs.
For dense graphs, if you assume a particular,
Some
like
structure.
some structure of the graph. Do you know the answer to this?
Well, for example, there's these results where you, on average, you can solve it in n squared time, for example. Like if you sample the weights from uniformly from a range from 0 to 1, then you can do basically quadratic time. And there's other results too.
So that's average over class.
Yeah, on average. For most samples.
I think there are also, if you assume something geometric about the graph, then you can also get some speed ups for diameter.
Oh, yes.
All right. Thank you for sticking around, and thanks, Nicole, for great talk.